All right, good evening, everyone. Welcome to Kopernik Observatory and Science Center. And tonight we have a talk on Fermi's Paradox, Are We Alone? You see that up on our website there. Before we get started with that, just a couple of things. Raise your hand in the audience if you are members here at Kopernik. Oh, good handful of you. Awesome. Just so you know, members at Kopernik do get in for free. They have free admission not only to our Science Center, but to over 385 plus science centers and museums across the United States and even some international ones. Most of it is free membership. They actually specify, I can show you on our member page, exactly what benefits you get at ASTC membership programs, and that science stands for the Association of Science and Technology Centers. If you go to this section on our website, you can click that link and it'll give you a really nice list of all of the science centers that participate. So that's just one benefit of several, including discount. If you're a Galaxy member, you get discounts on our classes, like summer camps coming up, which we have launched. We launched it back on March 16th. And if you come here to public classes and summer camps, you can get a whole list. They are filling up fast. A couple of them are even just about sold out. CAD Ventures is sold out, which is a middle school program. Immersive Innovators has one spot left. So if you're in grades 6 through 8 and want to delve into VR and VR development, there's one spot left. But there's spots in all the other camps for sure. And you can browse through there, and there's a registration link for online registration at the top. There's also in our lobby, we have some posters describing each of the camps as well. So one other tool I always like to show everyone, if you scroll down to the bottom of the page, you can access our clear sky chart. The clear sky chart indicates if we have clear skies, it's a weather forecast with astronomical context. So if we look over here on this side, breaking it down row by row, we have cloud cover. There's actually two cloud cover models, transparency, seeing, and then darkness. So cloud cover is the most important. We want dark blue across the board there, ideally, and tonight, it's a little iffy. Maybe we'll have some chance here this Friday evening. But it looks like there might be some clear skies coming our way next week, which will be excellent. So that's some of our website and the features there. If I bounce to this page, this is our YouTube channel. In fact, we are streaming live right now on our YouTube channel. So I'm going to wave to the camera up there that's watching me. So hello to everyone on YouTube. And we stream every Friday night program on our channel. So if you aren't able to come up on a given Friday night, you are welcome to tune in here. You can see we're live streaming this talk right now. And on top of that, we do cover astronomical events. So as an example, most recent example, we covered the total lunar eclipse that happened on Pi Day, March 14th. Lunar eclipse. And you can see we were streaming for 7 hours. This was not a super convenient one. It was very early morning hours, started at around midnight and carried on towards 6 a.m. But that's okay, because for you, we have the eclipse in a minute. So let me bring that up quick so you can watch it really fast.
Liberty.
Or you can watch an ad really fast. All right, we'll skip, and here you go. Eclipse in a minute. So this is what we call the partial eclipse, when the moon is just starting to enter the Earth's umbra, its direct shadow. And as you go through partial, you do start to see this red glow appear. Once you enter total eclipse, which lasts a lot longer than something like a total solar eclipse, this was an hour of totality here, and you get the red moon. And then eventually the moon exits the Earth's umbra, starts to brighten back up again, and this will only happen during a full moon, just like a solar eclipse will only happen during a new moon. So we got to watch the entire duration here, where we are at Kopernik Observatory. So the moon was already well above the horizon for us, and was just starting to get towards the western horizon setting by the end of it. So that's something you can tune in on our channel for as well. You can tune in on our live streams for observing, and we have a really nice community, a good chat going. We take questions. It's a lot of fun. So that's a bit about us, but now I'm going to bring your slide back up here. We're going to move over to Dr. Stanley Hunter's talk on the Fermi Paradox. Are we alone? So with that, I'll pass it right off to you, Stan.
Hello, can everyone hear me? That work? All right. Yeah, full disclosure, I'm not a physicist or a cosmologist or anything. I'm a medical doctor, but I'm interested in this stuff. It's very interesting. And this is a great topic. I think everyone's really curious about what's out there, who's out there, what's the use of all this inordinate amount of space around us. So I'd like to actually start with a couple of questions just to gauge where everyone is. With a show of hands, who out here thinks there's probably some life somewhere out there in the universe, but not on Earth, elsewhere than Earth? All right, that seems like almost unanimous. Not quite, though. Who thinks there is, let's see, multicellular life out there? Still, that's pretty good portions, definitely more than half. Who thinks there is like macroscopic multicellular life, something that would strike us as looking kind of like an animal? That's a similar number. Who thinks there's intelligent life out there? Life would say, some sort of a language. Okay, yeah. Who thinks there's technological life out there that might be able to use radio telescopes or fly off their planet? All right. And then I guess just the last one is interstellar civilizations. All right, now we're down to a distinct minority, maybe 15% or something. Believe there are interstellar civilizations out there. Yeah, so Enrico Fermi was an interesting guy. Let's just look back at where this started. So he was born in Italy, Italian born. He moved to the United States in 1938. He worked on the Manhattan Project. He was a really renowned physicist, and he was known for a number of things, one of which was he was extraordinarily good at doing calculations in his head. Almost the only person who was better was John von Neumann, who was perhaps the best who's ever lived at that. And Enrico Fermi, after working on the Manhattan Project, continued to work at Los Alamos. He became a professor at University of Chicago. And at one point, in 1950, he was having lunch with a few other physicists at Los Alamos. And one of them showed him this New Yorker cartoon, which was apropos for the time, because there was, in the current events in early 1950, a whole lot of garbage cans going missing in New York City, so apparently a theft. And there were also a lot of UFO sightings around 1950. And Fermi thought that this cartoon was a good hypothesis. It was parsimonious because it explained two problems with one assumption. Yeah. Let's see. So extraterrestrial civilizations. Well, I'm going to use this term many times tonight, and essentially what I mean, ETC, it's shorthand for an interstellar civilization, a technological civilization, a civilization that can at least do one of two things, and probably both: communicate across vast distances with radio waves or some other way, and travel across vast distances, like to other star systems. And it's hard to imagine, it's hard to judge these sorts of future or extraterrestrial civilizations and compare them for how advanced they are, because we're not one yet. We don't know what they're going to be interested in, what they're going to be aspiring to do. But Nikolai Kardashev was a Russian astrophysicist who came up with a scale, one scale, to compare these civilizations and get a rough idea of how advanced they are. And he based it on energy. Now, other people have done other types of scales, but he did it on energy. And a level 1 on his 3-level scale is a civilization capable of using essentially all the energy from a planet. So they could use all the incident solar energy, all the geothermal energy, all the other energy that's available on the planet, fossil fuels or whatever else that might be there. A level 2 civilization is orders of magnitude more powerful and can use all of the energy from a star. It's hard to capture the energy from a star, but some people have discussed ways that it might be possible. And then a level 3 civilization uses all of the energy from a galaxy, or is capable of using approximately that amount of energy. Other people's scales involved things like quantum technology, or the ability to do things with really small objects, like manipulate individual molecules, manipulate individual atoms, manipulate subatomic particles, manipulate whatever's smaller than that we haven't discovered yet. Other people have tried to make scales based on computing, like how many teraflops, whatever, you know, how much computational power they have, which would probably scale somewhat with energy or with their ability to manipulate tiny things. Now this would be from a level 2 Kardashev civilization, a K2. This is a picture from Next Generation Star Trek, and in this episode they discovered a Dyson sphere, which is essentially a sphere built entirely around a star to capture all of the energy coming out of the star. And so it was just a big dark sphere in space, not particularly obvious it's there. And that might be one reason why, if they're out there, we don't see them. They're hard to detect. They're far darker than stars. Now, a level 3 civilization, what would that even look like? They have all the power in a galaxy, and this guy just comes to mind because he pretty much can do anything he wants. Arthur C. Clarke, the science fiction writer, said that any sufficiently advanced technology is indistinguishable from magic. And a lot of the things we do would seem like magic to people from hundreds or thousands of years ago, and this guy does what looks like magic all the time. He bops from one side of the galaxy to the other, or to other galaxies, and comes back. He changes the trajectories of moons around planets, and all of it with a snap of a finger. So, for lack of a better example, he's a Kardashev 3 type civilization. So Kardashev and humanity, where are we on this scale? Well, Carl Sagan made a logarithmic version of this scale, and he said that we are probably about a Kardashev 0.7 to 0.8, and we might be 1 to 2 centuries from reaching a legit level 1 where we can use essentially all the energy available on our planet. Kardashev 2, use all the energy from the star. Well, this is a little harder because we can imagine how to use all the incident energy on the planet. We just need enough solar panels and enough, hydroelectric dams and so forth. But we have really no idea how to build a Dyson sphere or do anything else to capture all the energy around a star. But if you look at historically our energy use and you plot it on a curve, and you make it exponential and you extrapolate it, in 1,000 years, growing the way we are, we'll be in that order of magnitude, the energy of a star. And considering how far we've come in the last 100 years, it's not difficult to imagine we might be able to do that in 1,000. And then at level 3, how do you even estimate how long it takes to use all the energy of a galaxy? Well, it's got to be at least 10 million years because the galaxy is so big that even at the speed of light, it takes 100,000 years to go across the galaxy from one side to another. And you can do estimates for how long it would take to colonize a galaxy with assumptions like you travel at, I don't know, 10% of the speed of light, like really fast, but not quite to the point where your mass is increasing drastically. And maybe spend a few centuries at every planet you land on to colonize it and build more ships and then leap off from there. And if you just watch that wave propagate across the galaxy, within a few million years, conservatively 10 million years, a civilization should be able to fill up the galaxy. And that would sort of make us a level 3. So this is a picture of the Andromeda galaxy on the left side and the Milky Way on the right side. The Milky Way just looks like a stripe because we're in the Milky Way. So when we're looking in the plane of the Milky Way outwards, it's just a sort of stripe across the sky. Andromeda is a spiral galaxy that looks a lot like we would look to somebody in Andromeda. I mean, Milky Way and Andromeda are pretty similar galaxies. And that's about 2.5 million light years away. And here's Enrico Fermi again. So he was at this dinner or this lunch with the other physicists, and their conversation turned from that cartoon apparently to superluminal travel, or travel faster than the speed of light. And he and I think Kopernik were having a debate about whether we would get faster than the speed of light travel. Fermi estimated no, like 1 in a million chances, and yeah, he was a little pessimistic on that. And then their conversation turned to other things, and towards the end of the meal, Fermi just blurted out, "So where is everybody?" And the other people at the table immediately knew what he was talking about. He was talking about where are all the aliens, because they'd talked about aliens in the New Yorker cartoon. They had talked about the speed of light, which constrains how fast you can travel. They all knew the size of the galaxy and the number of stars in it approximately, because they're all physicists. And it was pretty obvious to Fermi that there had been enough time and there were enough planets out there that there should have been life evolved probably many, many times, and it would have had enough time in the 13.8 billion years of the universe, and back then they thought it was a little bit older than that, in order to colonize the entire universe, or at least the entire galaxy. So right now, estimates are usually 200 to 400 billion stars in the Milky Way. We can't see the whole thing very clearly, and there's too many to count directly. Almost all of those, because now we're actually looking for exoplanets and finding them all over the place. It seems like the rule is to have planets around a star. It's the exception not to have planets. So almost all of them have multiple planets. If you just multiply that out, 5 times or 2.5 times, 2.5 planets per star, there's over 1 trillion planets in the Milky Way alone. And probably 40 or so billion, give or take a factor of 2 or 3, Goldilocks planets, which is to say planets that are not so close to their star that they're just too hot to be conducive to life, and planets that are not so cold that they also wouldn't have life. Planets where water is likely to be liquid, and it's not always frozen, and it's not always in a steam or gaseous form. And just looking around, we've already found direct evidence of between 5,000 and 6,000 exoplanets with a few of our telescopes. And there's another one, the Nancy Grace Roman, coming online in 2027, which will be a very good exoplanet hunter. Yeah. And there are about 2 trillion galaxies. So if you want to extend this experiment, it would take a long time, like millions of years, to colonize the galaxy, to go from one side of it to the other. It would take a lot longer to go from another galaxy to this one. The closest galaxy is 2.5 million light years away, but the universe is 13.8 billion years old, 13.8 thousand million years old. So if a level 3 or civilization were in another galaxy for 1 billion years, they might just decide it's a reasonable hop to jump over to our galaxy. And with 2 trillion galaxies, well, the opportunities go up a lot. The Drake equation, this is Frank Drake up in the corner, is he came up with this mainly as a talking point. Oh, there you go. Mainly as a talking point for a SETI conference in 1961. And this is a rough way of estimating how many planets might be out there in the Milky Way with civilizations that we could potentially communicate with. These sorts of ETCs we're discussing. And essentially, if you multiply the number of the rate of star formation in the Milky Way galaxy, it's like 2 or 3 per year, times the fraction of stars that have planets, that's close to 1, they almost all do, times the number of planets suitable for a life per solar system, we don't really know that number, times the fraction of planets suitable for life on which life actually appears, we don't know, but we were starting to think it might be pretty likely, times the fraction of planets that develop intelligent life, times the fraction of planets with intelligent life that develop interstellar communication, times the length of time they last, you would get an estimate of how many civilizations are in the Milky Way. Now, Fermi was known for what are now called Fermi questions because he used to ask these all the time to grill his graduate students. And one that he supposedly asked was, he was at the University of Chicago, and he asked, how many piano tuners are there in Chicago? And that's a tough question to answer just pulling an answer right out of thin air. But if you think about it, if you live in Chicago, you certainly know the population of Chicago. You can estimate how many households are in Chicago, how many schools are in Chicago, what fraction of households/schools have pianos, how many pianos a piano tuner could tune per day, how many days per week a typical person would work. And if you multiply it all together, right, you get the number of piano tuners in Chicago. And if you multiply these terms, you get the number of planets in the Milky Way galaxy that have advanced life that we could potentially communicate with. There are other versions of the Drake equation too. Some people argue we should have additional terms like, well, if an asteroid wipes out life, or not all life, but wipes out the advanced life on the civilization, then maybe other life would take over quickly. For instance, it took almost 4 billion years for humans to get to where we are from the start of our planet's life. Our life started on Earth almost 4 billion years ago. But if humans were to go extinct, we already have like chimpanzees and bonobos and capuchin monkeys and some other pretty smart animals. You don't have to go through, fish and amphibians and lizards. And so maybe advanced technological life would happen in, maybe as little as a few million years or 100 million years, but probably wouldn't take another 4 billion years. So people have terms for extinction rates, colonization rates, so if they start to spread, then the number should actually increase, and rebound rates after catastrophes, and lots of other adjustments. But this is a really good first take on it. So now we're getting to the part of the talk which is, where are the aliens? Because when we look out there, we don't see aliens. We don't have any proof of them existing. But based on the Drake equation and some other back-of-the-envelope estimates, it just seems like they ought to be out there because the universe is big enough and old enough. And there are 4 classes of hypotheses. I sort of have them broken down into. The first one are all the hypotheses that say the aliens are here or were here already. The second one says, aliens exist and they're out there, but there's some reason that we can't see them. The third one says aliens don't exist. They're just, the reason we don't see them is they're not out there. And the fourth is some sort of simulation world. We all live in a matrix or whatever. I find the fourth a little bit less interesting, so I really don't spend much time on it. Because if everything's a simulation, then physics doesn't apply. There's no real rules. It's hard to do science in a civilization. In a simulation civilization. Great. So there are different hypotheses for why we don't see aliens. And one of them is that there is that they aren't out there, or that they, at least the civilizations that are able to communicate with us, don't exist, but there may be life out there. And or it could be that they just don't exist at all, and there's no intelligent life, including similar to our own, out there in the galaxy or the universe. And there are a bunch of filters, a bunch of steps towards the creation of humans, the evolution of humans, which are hard to get through. For one, it took on Earth 4 billion years to go from primordial sludge to us, and this lecture and me right now. And a star would have to live for all that time. The planet would have to have a stable orbit around the star for all that time and never get too close or too far, not get ejected from the solar system, and there couldn't be extinction of all life from an asteroid collision. You could kill off some of it because it'll rebound from that. And the moon helps us have a stable orbit or stable axis of rotation. And yet, if it takes 4 billion years, that might be uncommon because 4 billion years is almost a third of the age of the universe. There's also abiogenesis as a filter. So abiogenesis means the start of life from things that aren't alive. We know really well how evolution works. I mean, there's more to learn, but evolution works extremely well for explaining how we get from, itty-bitty worms to humans. But it doesn't work so well how you go from primordial sludge to the first cells. And there's a couple other steps, like how do we get more advanced cells, eukaryotic cells, where all of their DNA is crammed into the nucleus in the middle of the cell. It enables the cell to be larger, more complicated, do more elaborate things. But it's not clear how you go from a bacteria to a eukaryotic cell, or how you go from single-celled organisms like bacteria to multicellular organisms. Those are big steps. There's tons of hypotheses, and a lot of them plausible, but we don't really know how it is, and we also don't know how likely or unlikely these steps are. Are they inevitable once you have single-cellular organisms coating a planet, that they're definitely going to make these steps? Or are these really rare events that might take 1 billion years, and in our planet we're lucky and it only took 100 million years? You have to escape enough extinction events. I mean, I sort of said that before, but if the Earth gets destroyed by a collision with another object, like Theia, we ran into another Mars-sized planet, and that created the moon in the collision. It just blew off a chunk of Earth, which is now the moon. But if that had happened later on, after life had already started, turned the whole Earth back into molten magma for millions of years, life wouldn't have survived that in any form. Nearby supernovae could have done us in. Rogue stars, like a star just coming through our solar system, gravitationally stealing our planets or chucking them out into space. Stellar evolution, if the star dies or becomes a red giant on you. So there's a lot of ways that we didn't die. And then attaining technological intelligence, it's really complicated. How do we get these big brains compared to everything else on the planet? And it's a really long road. Even once you get to monkeys, to get from tiny monkeys or tree-climbing shrews, which are essentially our ancestors, up to modern humans. And there are a lot of steps that have to happen, but the development of thumbs and the use of tools, and then the use of language to explain how to make tools, and a cultural ratchet. So instead of everyone just having the instinct to make a good spear, someone can tell you with words how to make a good spear, and then everyone can make a good spear. There's a lot of things that have to happen on the road to having good technology. This on the left, these are pictures of what are called stromatolites. This is very early life on Earth. Several billion years ago, we have evidence of stromatolites, and those are cyanobacteria, so photosynthetic bacteria mixed in with clay deposits. And this is from Australia, but they still exist in Australia. And that was probably some of the earliest life on Earth and still around. Another great filter could be after us. So we've passed all these things, like getting from unicellular to multicellular organisms, but what if there's a filter in every society that gets advanced enough and has nuclear weapons or biological weapons or creates climate change? They all drive themselves into extinction. That is plausible. Nanobots would be nano-sized robots that basically just infect everything. Relativistic projectiles is interesting because in Star Wars, the Death Star was able to shoot a planet and blow up a planet. But really, if you took an X-wing and it could go almost the speed of light, and it hit a planet, it is big enough that at that speed it would destroy the planet. It would release enough energy, it would cause nuclear reactions because it would just fuse all the nuclei. An X-wing hitting a planet at light speed or very close to it would destroy a planet. So any civilization that can go between stars and can go at a substantial fraction of the speed of light could destroy a planet pretty easily. Artificial intelligence, well, that's a threat. Maybe they kill us off or kill off, their creators, or maybe they just merge with their creators and change the organisms so they aren't really what we would call living anymore. And then there's the nature of animals that conquer their planet. So any animal, human or otherwise, that conquers its planet is probably pretty competitive, likely started out as a predator. Predators tend to be smarter in the animal kingdom than prey animals. And maybe they just fight with each other like we fight with ourselves. So interpreting the great filter, there's all these possible filters. Does it make any difference which of those might have happened? This is Mars on the right, by the way. It might be better not to find life on other planets. If we look on planet and planet and planet, and we don't even find bacteria, well, that kind of suggests we're the only life around, at least around anywhere we've looked. I mean, we can't look everywhere in the universe. And that would sort of imply we're past the filter. And if we found really simple life, like bacteria or other single-celled organisms, then that would suggest we're also past the filter. But if we were to find life that's pretty advanced, like, life with jungles and cats and monkeys, or things that look sort of like that, or the life like the movie Avatar, that would not be so great, because if we got to this point and they got to a point similar to ours, and we don't see any civilizations that have gone interstellar, it suggests that maybe one of those filters that's after us is a really strong filter. Yeah, that would suggest an imminent filter for us. Is there a flaw in this whole great filter idea? Well, I don't know if there's a great flaw in it, but the filter would have to be perfect, because if you think about it, for billions of years, if civilizations had been getting up to the cusp of spaceflight like we are now, and if even one of them managed not to drive themselves into extinction, they would have the opportunity in a mere few million years, a cosmic blink of the eye, to populate the entire galaxy. So a great filter, in order to be an explanation for why there are no ETCs, has to be almost a perfect filter. And once a civilization is interstellar, once it inhabits multiple star systems, it really doesn't have very many threats to its existence. I mean, it has the threat of itself. It has the threat of if it gets into internecine warfare, if it has infighting among other members of its own civilization, well, that would be a threat to its existence. And I suppose another extraterrestrial civilization could be a threat to it. Things like stars drifting wouldn't really, or stars evolving wouldn't, stellar evolution where a star turns into a red giant or something, wouldn't really be a threat to it. They already live on multiple star systems. They can hop to other star systems if they need to. But another ETC could potentially be powerful enough to destroy an ETC, but in that case, the filter has already failed because there's another ETC, a bigger, badder ETC out there. Which leads us sort of to the dark forest hypothesis, which is so named because it's sort of a metaphor to if you find yourself in a dark forest as a little predator, do you really want to draw attention to yourself? Do you want to make your little roar and risk that a much bigger predator, its attention is drawn to you by that? If there are super powerful, malevolent ETCs out there, maybe the smartest thing is to keep your mouth shut and try just to hide and not draw attention to yourself. So that's the dark filter hypothesis. A dark forest hypothesis, which really isn't quite a filter because it suggests ETCs exist, including multistellar ones that have colonized most of the galaxy, but a lot of them are just strategically silent. Why would they be strategically silent? Well, because these civilizations are so powerful that space wars would be like first strike, winner takes all. because with one relativistic projectile or a laser beam from a Dyson sphere capturing all the power of a sun, I mean, you could destroy a planet so easily. And that creates what's called a Hobbesian trap. A Hobbesian trap is basically a situation where your incentive is always to attack first. If you attack first, you know you win. And if your opponent attacks first, you know you lose. And so everyone gets sort of a hair trigger. And foes could be also eons ahead of you in an arms race. I mean, what chance would a Civil War army or even a World War II army have against our smart bombs and nuclear weapons or whatever of today? None at all. And what chance would a Revolutionary Army have against the World War I era army? None at all. And what chance would chariots of ancient Greece have? And that's only separated by a few centuries or maybe a couple thousand years. They could be billions of years ahead of you. You don't want to fight with the Q continuum. So problems, how do they all know to stay silent? It's not obvious to us that we should stay silent. I keep touching that. It's not obvious to us that we should stay silent. In fact, we're leaking a lot of radio waves into space all the time and have been for most of a century. And advanced ETCs could find each other anyways. I mean, if this ETC has populated the entire galaxy, it could send probes to every star system and it would know you're there, whether you're broadcasting your presence or whether you're trying to hide. And why would the boss ETC, why would it be silent? It has nothing to fear in the galaxy. And then Carl Sagan actually said, this whole thing doesn't quite make sense because any ETC that managed to jump off its planet and spread throughout the galaxy and not kill itself off it's probably learned how to exist peacefully. So it's a peaceable civilization. So it's not evident why the dark forest is necessarily the situation. Another hypothesis is that space travel is impossible. So this is a picture of Earth taken from Voyager 1 from 3.7 billion miles away. And Earth is this little tiny white dot right there. It's only a few pixels. And it's just hanging in space. And that streak is just an artifact of the lens. And maybe space is just so big that it's not realistic to cross space, at least as a biological organism. Too far, takes too long, too many lifespans. Cosmic rays can destroy DNA and cellular walls. They're just like charged particles moving at almost the speed of light. Propulsion through deep space, there's a lot of ideas about how we might be able to do this. None of them are proven. Chemical rockets don't work. You run out of fuel, they're not fast enough. And sort of nuclear rockets are a thought, but you need something to propel out. So what do you use for fuel to propel? Maybe you can collect hydrogen in interstellar space. Maybe that doesn't work. Collisions at relativistic speeds. If you hit a pebble, a space pebble, and you're traveling at a quarter of the speed of light, that's bad news for you. And if you don't go at a substantial fraction of the speed of the light, you'll almost never get there. This wouldn't preclude, however, mechanical probes. You could send mechanical devices and computers and maybe AIs out there, and you don't have to protect their DNA because they don't have DNA. They could be smaller and could be shielded, so it still would be possible for an advanced civilization to populate the galaxy. There are also some thoughts about resource limitations. The light cage is an idea that if your population and its resource needs grows at an exponential rate, then even if the amount of territory and the resources that you own is expanding like a sphere, expanding with the radius traveling at the speed of light, the radius increasing at the speed of light, an exponential growth curve will eventually pass even the volume confined within that light sphere. But lots of species live on islands for millions of years. The solution to that is you just can't have exponential growth. At a 2% growth rate within 3,000 years, your civilization would outrun a light sphere, but that just means you can't have a 2% growth rate for 3,000 years. Humanity has a growth rate of about 1% now. And then there's the nature of aliens. Maybe aliens are just not easy to recognize. They could have all different forms, and that might not be obvious to us. Maybe they're not carbon-based. If they're silicon-based, maybe we would be able to notice that. If they move around and make themselves obvious that way, we might get an inkling. But Carl Sagan described potentially gaseous life forms that could live in gas giants that are sort of like clouds or bubbles, and they could change their buoyancy and go up and down and have energy cycles and metabolisms. There could be machines that sort of replace us or merge with us, or replace other extraterrestrial life forms, such that you have essentially post-biological life forms. And they look more like computers or something, and it's not obvious that they look like living things. In this Star Trek episode, Beverly Crusher is interacting with an anaphasic life form, anaphasic energy life form. It's a life form that supposedly exists as fluctuations in an energy field. And it took them a long time in the episode to realize why their ship was acting funky, because there was this life form on board. And maybe it would be hard for us to notice if that life form were right underneath our nose either. And there's no hard rule to say that that kind of life form can't exist. I mean, it really just needs to reproduce, evolve, carry out some life processes, and you could call it living. There's something called a zoo hypothesis, in which, the life forms are out there, the ETCs are out there, but they're just watching us. They're not communicating with us, they're not talking with us, sort of like zookeepers in a zoo. And maybe they don't want to communicate with us because we're not that interesting to them, or maybe there's some sort of like a prime directive and we're not ready yet. I doubt they would fear us, they're too far advanced from us. But the problem with that is the zookeepers don't hide from the zoo animals. Some people say maybe this is an argument for active SETI. So instead of pointing your radio telescopes at the sky and looking for signals from extraterrestrial civilizations, we should be broadcasting signals trying to catch their attention. Because if the animals are waving at the zookeepers might be more inclined to interact with the animals. Maybe they're not interested in us because, if they're billions of years ahead of us and they have computer-augmented brains, then we just aren't smart enough. They've already figured out all of physics. They know how to do anything they want to do. They have magical-like powers. So we don't really aspire to talk to slugs. So maybe they don't really aspire to talk to us. Now, Dyson spheres are kind of hard to see. So that's the sphere you build around a sun or a star to capture all of its energy. But then the sun doesn't radiate brilliantly into space. A Dyson sphere, it can't be absolute zero. It has to have a little bit of temperature on the outside, but it would be a lot more discrete than a star. So some people say, well, they're out there, but it's hard to see a Dyson sphere because they're dark from the outside. And maybe we're looking in the wrong place. Maybe these super advanced civilizations don't care to live around stars. If you lived around a black hole, there would be a lot of energy sources. And one advantage to living around the black hole is if you want to communicate with another civilization on the other side of the universe, you can use time dilation. So you send your message to it, and then you hang out near the black hole where time travels very slowly for you, and it seems like your probe is moving much faster than the speed of light, when it's really not. Or at the edge of the galaxy, there might be better real estate for certain types of thermodynamic engines. There's another hypothesis, another thought, that maybe we're just not looking correctly. So SETI is looking for radio waves. We use our radio telescopes to look for radio waves, but maybe in a million or a billion years, we won't think radio waves are the best way to communicate. Tachyons are a theoretical particle. We don't know if they really exist, but their thing is, if they do exist, they travel faster than the speed of light, and that would be a really good way to communicate. Gravity waves might be able to send signals. We know gravity waves travel at the speed of light. Quantum entanglement, there's lots of stuff about this. If you have two particles, you can figure out, you can create particles so that their spin or some part of their orientation is opposite each other. But if you observe one, you know that the quantum wave formula collapses for the other one, and yet there's always like a catch-22. The the particles are random, so you can't really send information by looking at entangled particles. But if they figured out how to do that, that would be an awesome way to communicate at essentially infinite speed. And neutrinos are interesting. Neutrinos are sort of like photons, but they're not light. But they don't interact with anything, almost. So they can go through like a light year of lead, and most of them don't even interact with the lead. We do have neutrino telescopes that can detect neutrinos, though, and we do have neutrino emitters, so we can send and detect neutrinos. And if they can do that, maybe neutrinos are a good way to communicate, because they go through everything. They can go right through a star. They can, well, not a black hole, but they can go through almost anything else and not be slowed down and not be blocked. Go through gas clouds in outer space. Or maybe these extraterrestrial civilizations do use electromagnetic radiation, but it's hard to detect it for other reasons, one of which could be they're just really far away. When you have any sort of light radiation, electromagnetic radiation, things like light or radio waves, if you go twice as far away from the emission source, the power goes down by a factor of 4. If you go 10 times as far away, it goes down by a factor of 100, 4 squared or 100 squared, or 2 squared or 100 squared. There's an inverse square law. And when you're talking about distances that are many light years, that inverse square law takes the transmitted power at the receiver almost down to 0. So it's been estimated that if you had one of the largest radio telescopes on Earth on Pluto, you could barely detect any of our radio frequency emissions. We can barely get our signals out of our own solar system. And from a light year away, we wouldn't even be able to detect ourselves, because the signals just aren't strong enough. If you had like a laser beam, though, a laser beam doesn't weaken nearly so much when it goes a long ways because it doesn't spread out through space. So maybe they communicate with something like laser beams or extremely directional radio antennas. But the problem with that is we're not going to happen to see it by listening with SETI, because unless you're in the path of the laser beam, you just can't see it. So lasers would be efficient, but yeah, hard for a third party to notice. And it could also be hard for us to notice, even if we were picking up some of their transmissions. If you have really well compressed data, it kind of looks like random noise. I mean, if there are patterns in the data, it's not fully compressed, because you could take those patterns out and compress the data even more. So maybe some of what we think is static could be signal. So probes. Probes are an interesting way for extraterrestrial civilizations to gather information. They could tolerate interstellar travel because they're not alive. This is a probe from, I think, Empire Strikes Back, yeah, the beginning, looking for the rebel base. They could do lots of work for you, like reconnaissance, mining, terraforming, construction in outer space. They could be very discreet. I mean, some people say if there are probes in our solar system, why don't we see those? But what's to say they're big? I mean, this thing, I think it's probably only like 4 feet high or some. And if it were on our planet, we might not have found it. And if it were cruising around our solar system in the asteroid belt watching us, we certainly wouldn't have found it. So they could be really discreet. They could also maybe even be physical messengers, which I'll get to in a second. There are things called Bracewell-von Neumann probes. Some people just call them von Neumann probes. Von Neumann is the guy here on the left, and Ronald Bracewell, John von Neumann on the left, Ronald Bracewell on the right. John von Neumann was a Hungarian-born mathematician and physicist and chemist and computer scientist, and he discovered a zillion things. There's so many things named after him, including 4 things named von Neumann machines, that we don't just call these von Neumann machines. So von Neumann studied how machines could replicate themselves. You could make a machine that could just go out into its environment, mine materials, and find ways to build its own copy of itself. And then Ronald Bracewell was an Australian-born electrical engineer, and he did a lot of advocating for using probes to explore outer space, because they're cheaper, they're a lot safer, they can go farther, make the missions faster to bring to fruition. And he wrote a paper about that in 1960, so they put his name with von Neumann for these self-replicating probes that explore space. And if you assume the probes travel at 10% of the speed of light and spend 500 years on every planet they get to, in a few million years, less than 10 million, they've gotten every planet in the entire galaxy. Now, physical messengers, they could, instead of sending radio waves to communicate, you could send probes with information. And the bandwidth is actually really high because, you know, we have terabyte SD cards. And, you know, they could have way more than a terabyte on something smaller than our SD cards. And if you sent that, it's so small, at a high fraction of the speed of light, maybe it's not going at the speed of light like a radio wave, but it's going close. And when it gets there, it has a tremendous amount of information. And if you want to do error checking in your message, like a checksum, and say, yeah, I didn't hear that part, it was fuzzy, send it again, well, that's great if you're on the same planet, but if you're light years away, that's a long delay. But if you're sending a little chip with all the information, it gets there, and it gets there incomplete. I mean, it stays there. It's not like, and if your receiving telescope goes offline for a few seconds, that part of the radio signal is way past you, and there's no getting it back. But if you have the little chip, you have the whole thing. So physical messengers actually might be a reasonable way to send data through interstellar distances. Yes, so they self-replicate. Risks. Berserkers are a certain kind of von Neumann probe where they don't just go out there to explore, they go out there to kill planets. That's sort of a nightmare scenario. And there's also the idea that they might just fill the galaxy. I mean, some people have said, well, we don't see von Neumann, Bracewell von Neumann probes because a really smart ETC wouldn't make them because they would realize that if they got loose in the wild and their code mutated and they just started reproducing, in a few million years, they would have filled the galaxy or discovered all the planets in the galaxy, and in a few million years beyond that, they would have turned all the resources in the galaxy into more probes. Yeah. Well, I don't know if that's compelling. Like, we use dangerous technology. You just have multiple safeguards. But that's a thought. There's also the rare Earth hypothesis. Why don't we see life out there, or at least extraterrestrial intelligent life, communicating with us? And it's because the Earth is so unusual. And the Earth has benefited from many factors. First off, there's a lot of water on Earth, and as far as we know, water is necessary for life. There might be other forms, but all the life we know needs water, and Earth has that in spades. Earth is rich in metals, and by metals I mean everything that's heavier than hydrogen or helium, like sulfur, phosphorus, oxygen, nitrogen, carbon, and those molecules are really useful for making organic structures, which are super complicated and can be large and can have elaborate chemistry that begets life. Earth is about the correct size. If Earth were 1.5 times its diameter, it would probably be so heavy that it would trap hydrogen and helium, and it would start to have sort of a gas giant composition. And if it were smaller, like less than 2/3 of its radius, it might have a hard time holding any atmosphere at all, including CO2 and water, vapor, and nitrogen, and some other things that are kind of sparse on Mars, because it's not all that big. It does not have a dense atmosphere. Earth has plate tectonics, which actually are really helpful for life. One thing they do is they help with the carbon cycle. So what happens with all the carbon on the planet? If it goes into the atmosphere as CO2, the planet warms up. If all the planet's carbon is sequestered and not in CO2, the planet cools down. And there have been at least 2 events in Earth's history when the Earth, maybe it got a little further from the sun, or maybe through a fluke and lowering CO2 levels, it got pretty cold, and the ice caps got down to the equator, and then the Earth was pretty much a snowball. It was white, and it had a really high reflectivity called albedo, and when it turned white, it reflected so much of the sun's energy off, it cooled down even further, and they call that snowball Earth, and we think it happened a couple of times just under 1 billion years ago. And how does Earth even escape from a snowball planet? Like, life can barely survive on a snowball planet. It has to survive around like geothermal vents, or maybe there's spots where the ice is clear, but we think the ice was probably kilometers thick everywhere on the Earth. So what happened is the volcanoes just kept on having their tectonic activity, and they kept on spewing carbon dioxide into the atmosphere. And with no plants to fix the carbon, because everything was covered, or not many plants, everything was covered in ice, and with no rain, because all the water was already precipitated as snow, with no rain, there wasn't liquid water available in the atmosphere to turn the carbon dioxide into carbonic acid and take it out of the atmosphere. So the CO2 levels just rose and rose until we had a greenhouse effect and it melted the snowball Earth. So plate tectonics and volcanic activity spewing out CO2 saved us from what would have been kind of a terminal freeze-to-death planet situation. So that gives us really good climate stability. We have a great magnetic field because we have a liquid ferromagnetic core. The two most ferromagnetic, or magnetic essentially for short, elements are iron and nickel, and that's what our core is made out of. And it's liquid and it keeps on moving, and our magnetic field is quite active, and that deflects a lot of charged particles coming in from outer space, from the sun mainly, which protects us from having our DNA damaged. Our sun is a main sequence star, so it lives a really long time, and for a large fraction of that time, it doesn't get much brighter and it doesn't get much dimmer. It's just the same approximate power output. And that steady power, combined with a good distance, really helps Earth. I mean, if your sun is getting brighter and dimmer, unless you can change the orbital radius of your planet, you're going to get cooked or frozen at some point. And so we have a good star for that. I mean, it's not an unusual star. A lot of stars are main sequence stars, but it's a good star for that. And it's kept a good power output for over 4 billion years. We are in the Goldilocks zone, but not just the Goldilocks zone, which means that we have liquid water. It's not frozen or gaseous. It's also been continuously in a Goldilocks zone for 4 billion years. And we're also in what's called the galactic habitable zone, which means we're not near the center of the galaxy where stars are super dense, and it would be unlikely to have a stable solar system for a billion years, because when the stars are really close to each other, they're passing each other and gravitationally whipping each other around, and some other star comes by and just steals the planets or flings them off into outer space like a big gravitational slingshot. So if you're too close to a lot of other stars in the dense part of the galaxy, maybe that's not suitable. So we're in the galactic habitable zone, and we've been the entire 4 billion years. The moon helps us with the stability of our axis of rotation. The Earth-Moon unit has a much larger moment of inertia than the Earth would by itself. Other planets that don't have moons, like Mars, really, because Phobos and Deimos are puny, they're just little boulders. But they're not big enough to stabilize Mars's axis of rotation, so over hundreds of thousands or a few million years, Mars's axis just keeps on shifting. But Earth's has been stable for billions of years. The moon gives us tides, which is a nice mixing mechanism, because what do you do in a biology class when you inoculate a tray or a medium, an agar? You mix things so that the life can expand. The moon is the correct size. If it were smaller, it wouldn't have the correct effect. If it were larger, its tidal effects could be destructive. And it also goes in the right direction. Some theories propose that Venus was struck by another large planetoid, and it had a moon for a little while, but Venus's moon was going the opposite direction of Venus, the planet. And so instead of the tidal forces, as in our case, slowly pushing the moon farther away from us, with Venus, it slowly pulled the moon closer to it until it had another super collision, and that would not be good for life. We have Jupiter. It's really complicated what Jupiter does. It probably protects the inner solar system from lots of objects coming from the outer solar system, but it also sometimes knocks asteroids out of the asteroid belt into the inner solar system, and we have about the correct number of extinction events. Correct for creating advanced life, or life such as us. Because if you had, too many, life would never get a foothold. But if you don't have enough extinction events, evolution would just have an equilibrium. So evolution sort of advances, big picture, by like a punctuated equilibrium. Dinosaurs ruled the Earth for 180 million years or so, and then an asteroid killed off them. There were no top predators, no super predators, and so the mammals, which were tiny, started to evolve into open niches. And that was a whole different type of life that evolved in the last 65 million years. But if the dinosaurs hadn't died, we'd still have dinosaurs. And the Earth has had 5 major extinction events in its 4 billion year history. And it gets hit by a multi-kilometer size asteroid about once every 100 million years. Jupiter helps with that frequency, and that's probably about the recipe for the optimal number of large but not complete extinction events to foster diverse life. This, by the way, this little arrow here is pointing at Earth. This is Earth, a picture of it taken by the Cassini probe when it was in orbit around Saturn. So that's Saturn up close, Saturn's rings, and Earth in the distance, that little speck out there. And that was taken in 2004, I think. All right, so this is the last few parts of the last few slides of the talk where I'm essentially going to say what I think is the most likely explanation for the Fermi paradox, because I've read about this for a long time, and some of the stuff seems plausible, some implausible, but the paradox remains. The universe is so big and so old, why don't we see life? And I gave a few hypotheses here, but I don't find most of them compelling. I'm going to go by category of hypothesis. So either they are/were here, or they're out there, but we can't see them for some reason, or they're not out there. And they are/were here is the easiest one to dismiss. Before I go farther, by the way, I'm going to tell you what I think is the most likely resolution of the paradox, but if you can convince me otherwise, go for it, because it's not the solution I want to be true, it's just the one that I think probably is true. And you'd make me happier if you could dissuade me from my conviction. They are/were here, so this is pretty easy to dismiss, because aliens existing among us would be a pretty extraordinary claim. And extraordinary claims require extraordinary evidence. Carl Sagan said that eloquently, but even before he said it, it's sort of a foundation of the scientific method. If something is truly against all your prior assumptions, intuitions, your knowledge of how the world works, you should really demand high evidence before accepting it. Because if you don't require really strong evidence to believe something extraordinary, you're likely to end up being extraordinarily wrong. It's only a matter of time until you are. So, yeah. So it's pretty important. And I think the evidence for aliens among us is pretty poor. The claim is almost as extraordinary as like magic and miracles and all that stuff, but the evidence is really abysmal. There's like dubious eyewitness reports and insinuations and blurry pictures that almost look like they're ancient or old technology with like, pots and pans held up by strings. So I'm just not convinced by that. A cover-up doesn't make sense. People just can't keep secrets, let alone huge government agencies keep secrets. So moving on. Do they exist, but we can't see them? This one is really tempting. It's harder to dismiss this one for 2 reasons. One, most of the Fermi paradox solutions that I talked about in this talk, and just in general, explain the paradox by saying they're out there. There's just some reason, usually a catch-22, that we don't see them when we look for them. The other reason is, Demosthenes said almost 2,500 years ago, that what one wishes, one is quick to believe. It is easy not to scrutinize these and to just follow them because, golly, that would be romantic to think that they're out there and we are imminently going to join this interstellar community. So that's tempting. But we also have Occam's razor, which is, of multiple explanations, the simpler is generally to be preferred. And if you look out there for aliens and you do a few experiments and you don't see the evidence you thought you were going to see, then probably they're just not there. And if you find yourself doing experiments, the experiments failing or making predictions and then observations, and the observations failing to bear out your predictions, and then you find yourself making contrived explanations as to why that's what you would have expected in the first place, and you keep doing this, I think you are likely somewhere between fantasy and motivated reasoning, and that's a real trap. So I think if we don't see spacefaring ETCs and their radio telescope signatures, it's probably because they're not out there. That said, there are, I think, civilizations like us, and we don't count yet as one of these ETCs. Our radio signals barely get a light year away from Earth before they're so severely attenuated they won't be heard. And we can go to the moon and we can send a few probes to Mars. We're just not interstellar, but maybe we will be at some point. And then the third category is they don't exist, and I think this is the most likely. When I say they don't exist, I mean the interstellar civilizations don't exist. Certainly civilizations kind of like ours, and animals like any animals that have lived on Earth, roughly like them, probably exist all over the place. This dump truck has a payload capacity of somewhere around 55,000 pounds, and that's sand. And the number of grains of sand in that dump truck is somewhere between 10 and 15 billion. I mean, they haven't standardized the size of sand grains. But that is 10 to 15 billion grains of sand, and we think there's maybe 40 billion Goldilocks planets. That's like 2 or 3 of those dump trucks worth of Goldilocks planets in the Milky Way alone. And if life evolved in another galaxy, even if it was hundreds of millions of light years away, but it evolved a few billion years ago, and the universe is almost 14 billion years old, so someone could have beaten us by 10% and evolved a billion years before us, or 1.5 billion years before us. They could have come from another universe, from another galaxy. And there are 2 trillion galaxies, so you would need several trillion of these dump trucks to show with grains of sand the number of Goldilocks planets we think are probably out there in the observable universe. And if you want to know what 2 trillion of these dump trucks look like, it would be the entire surface of the Earth, including the oceans, covered in those dump trucks, just stacked right next to each other. Not on top of each other, just next to each other. But that's a lot of dump trucks, and that's a lot of sand, and that's a lot of planets. I think that humans have made the error many times of being too anthropocentric. They think that we are somehow special in the universe. We thought that the Earth was the center of the universe and everything went around us. We thought that the sun was a unique star, that it wasn't an average main sequence star. We thought the sun was the only star that had planets around it. Turns out, now that we know how to look for them, almost all of the stars have planets around them. We thought that the galaxy was the entire universe. Turns out there's a couple trillion other galaxies that we've been able to find. I mean, with the Hubble and James Webb. We may find more later. It seems cosmically narcissistic to say that we are unique. So I don't think we're unique. I think there's classrooms something like this speckled through the galaxy and certainly through the universe. And yet, it's hard to deny after most of a century, half a century plus of looking, that their signals are not obvious. So what does that leave? That leaves that there's a pretty good filter, and that filter is between us and spacefaring civilizationhood. And at our current trajectory, I feel like, Star Trek again had it right. Maybe by the 2300s, we'll be bombing around between stars in probably not warp speed, but pretty fast spaceships. That doesn't give us a whole lot of time. I don't think there are any laws of physics that preclude us from getting off this planet and to other stars. I don't think there are any technical barriers that we cannot surmount. But this left me looking and trying to do some highly motivated reasoning, I might add, to console myself that we are not likely to go extinct. But there's just so many reasons why we might. And if you look at the Drake equation, that last term, L, is how long a civilization lasts. We know a lot of the terms. We know how many stars there are. We know how many planets around a typical star. We have an idea how life evolves on a planet, how it starts, how evolution works. We can fill in most of those variables, and we get really big numbers for the number of planets that have life on them with most reasonable assumptions. But we just don't know what L is. Does one of these civilizations last for a century or two, or does it last for billions of years? And that one term can make the whole equation virtually go to zero. So yeah, I think we can solve the technical challenges, but I'm more concerned whether we can solve the problems of our own psychology. And, oh yeah, there's the Copernican principle. We're not privileged. We're an average planet. And that's Earth, not really from the moon, from a spaceship orbiting the moon that was taken on Apollo 8 and they didn't land on the moon. But that's Earth out there all by itself. Thank you, I'm done.
Hi. I'm Drew Desker. I'm the director here, and I had a previous engagement earlier, so I missed the welcome. But thank you so much, Dr. Hunter. Do we have any questions out here in the? Well, okay. I guess whatever questions you had, you've already answered them, I guess. And
I have a sort of interesting question. I mean, at the beginning, we held up hands. How many people think that there is life of some sort somewhere in the galaxy, and multicellular life, animal-like life, sort of intelligent life, a la us? And I wonder if anybody has changed their opinion or their view on that, and if they'd be willing to share, maybe why. Or convince me why I'm wrong.
actually, we took a poll on the YouTube chat.
Oh, sweet.
Yeah, so with 12 votes in, we just had a short question of, are we alone in the universe? And the yeses are 17% and the noes are 83%.
Yeah, so I think Are We Alone in the Universe really needs to be divided in, are there other animals out there, including relatively smart animals, or are there interstellar civilizations which could possibly communicate with us or visit us, or we could talk to in the future? But if they're like us and we're like us, we're just too far away. We're on opposite sides of an ocean and we can't talk. So yeah, that's two different kinds of questions.
Yeah, go ahead.
All right, so we also have a question from the live chat. Mike Blake asks, any thoughts on gravitational wave modulation by K3 civilizations?
I mean, a K3 civilization can do whatever it wants. From my understanding of gravitational waves, I put it up there because a few authors mentioned it. I don't think it sounds super promising. Unlike electromagnetic radiation, like a laser or even a high-gain radio telescope, you can't direct it in one direction. If you just wanted to broadcast something out in all directions, maybe a gravity wave would sort of make sense. It does travel at the speed of light, but to make a good gravity wave, you need to do some pretty high-energy things like collide black holes or neutron stars. It would be so much easier just to make a radio telescope or a laser, or a tachyon, or not a tachyon, a neutrino telescope, if for whatever reason you wanted to, aim it right through things. So I don't think gravity waves sound super promising, but I'm willing to be convinced otherwise.
All right, we have a couple of questions out here. We'll bring the mic out.
This is just about your picture that we have up there, or the picture. There are two bright spots, and you can sort of tell where the sun is in relationship to us.
Yeah.
Are those planets that are visible?
No, I think
no,
those are
they're-
stars.
Those are stars. Okay.
Yeah. I don't know the focal length of the lens they used to take this. It was something of a zoom lens, but my guess is that they're off of the ecliptic. But I suppose I could be wrong. My guess is they're stars, though. Drew, do you know? You might know that.
I'm trying to look it up.
There you go.
But meanwhile, we do have another question.
In terms of your own feelings, would you prefer that our the perceived silence that we have in our galaxy is a result of the dark forest hypothesis, or because the great filter lies beyond where our civilization has achieved?
Oh.
What reality would you prefer to be in?
I think, it's funny because they're both kind of bad news situations, but it's actually kind of easy. I think the dark forest would be better. We haven't blown our cover yet because we're just not using powerful radio telescopes, radio transmissions yet. And the dark forest, it could be a long time until they find us, and I don't know, maybe we can smooth talk our way out of it. But the filter, if it's a filter with very few, that nothing gets through, that's imminent. That's like in a century. I mean, it could happen tomorrow. We have the technology to do it now. And given the way technology increases, that just seems so imminent. The dark filter, even if they'd already trained the laser on us, it's likely they're more than 100 light years away. I think the dark forest is probably preferable. Yeah.
All right, another question.
Not so much a question as sort of an observation. I've always been fascinated with the idea of the expanding universe, and the factor that seems to me to militate even ever contacting, if there were to be some other civilization out there, anything of intelligent life, is that the distances are so great. And the reality that when we look at the night sky and the stars that we see, we're not even sure some of those things are still there, because it has taken so long for the light to get here. We just have no way of knowing that what we're seeing right now still exists. Huge distances that are simply mind-boggling and leave me just in sheer awe of what there is and what we do know, and a real sense that there's a lot that we're never going to know.
Yes, there are some distances from which light took so long to come that we don't know if those stars are still existent. If you want to talk about those distances, though, you're talking about things well outside of our galaxy. Andromeda, the nearest galaxy, is 2.5 million light years away. 2.5 million years is nothing on cosmic scale. It's not even much on evolutionary, like biological scale. It's nothing compared to the age of our planet, which is 4,000 million years, and 4,500 million years. So you're talking about things that are so far away, they're either essentially out of our light cone. They're so far away we could never get there, and they couldn't get here. Even if some of them we can see them. We know that they were there. We have indication of their existence. But when you're thinking about the Fermi Paradox, it's enough to make the paradox tantalizing that the Milky Way is small. When you're talking about cosmic or even biological evolution time frames and the size of the Milky Way, it's small. 100,000 years to cross it is really short. Like humans have been a species for 2 or 3, depending on how you count it, 100,000 years. And our hominin ancestors, since Lucy, Lucy is over 3 million years old, and our last common ancestor with any other existent primate, like chimpanzees, is around 7 million years old. So 100,000 years just doesn't seem like a long time. So I totally agree with you that the distances are mind-boggling, including the distances to nearby stars. But for the purposes of the Fermi paradox and why aren't they out there broadcasting their presence, the Milky Way is small.
All right. Well, if you have any other questions, Dr. Hunter, I'm sure will be hanging around here. We have a rule here that you can't leave Kopernik until you look through a telescope. So you can place your keys on the desk over there. And anyway, we actually have been able to see the moon. And so especially if you've not looked through any of our telescopes here, we invite you to head out. You go through those double doors that's straight across the lobby and go to the left. And there's a building entrance to the right. And so head on in and we'll get you to check out the moon through one of our scopes. All right. Next week, our talk will be about AI and the use of AI in classrooms. It'll be presented by Dr. James Pederisi of Binghamton University, and also an engineer out of Raymond Corporation, talking about AI. And so thank you again for coming up, and look forward to seeing you up here and often. All right. Thanks again, Dr. Hunter.